Just making sure everything's working. I'm hoping that the volume is a little better today. I'm going to try and put the microphone like inside of my mouth just so it can actually pick up my voice, because it didn't seem to be doing that last time, which is kind of weird, but we'll try it today. So yeah, today we are going to be returning to our math library. I'm kind of just shooting the shit with, I'm going all over the place with this math project. We did a little bit of graph theory shit, but we didn't do too much, so I want to do some more there, but I do want to do some encryption stuff first, just because I figured this out, and it's pretty cool. So we're going to try that today, or right now rather. So yeah, first we are going to talk about a little bit about AES, what it is, a little bit of the math behind it, and then we will actually start writing the algorithm. I'll just open up OneNote real quick. AES. This is going to be Galwa. Alright, so let's start in OneNote with this. So today we're first going to be talking about something called Galwa Fields. This is a different type of math. Probably haven't heard too much about it if you haven't taken any discrete structures classes. I even took a discrete structures class, and we didn't even talk about this. But anyway, so we will talk first about what a field is. And then we will talk about Galwa fields, which are just pretty much just the same as a field. So field, also known as a finite field, or a Galwa field. So any one of these names. And then we'll talk about two types of the Galwa fields and how they are used in the encryption algorithm. So a field, in its simplest way, we're going to use GF for Galwa fields, and it's going to have a parameter n. It's just a set of n elements. And these elements are bound by 4 operations. So let me reorganize this actually. So bound by 4 operations. There's addition, subtraction, multiplication, and then inversion or division. But we're going to call it inversion. And the conditions on these operations is that they have to produce a result that is also in the field. So for example, if we had an A plus a B, and this gave us a C, if A and B are in the Galwa field, then C must be in the Galwa field as well. So any kind of operation, you can kind of think of this as similar to spans if you know what those are from linear algebra. Essentially, anything that we do to these numbers using the defined operations, however we define them, they just have to be within the same field. So one type here of Galwa fields that we know, that we're going to learn about, is called a prime field. And this is GF with P elements. So P elements, and these P elements are going to be just the integers from 0, 1, all the way up until p minus 1. So p elements, so we go 0 to p minus 1. So those are the elements in the prime field, and the arithmetic operations here are pretty simple. So for addition, subtraction, and multiplication, we have that a plus minus or multiplied by b gives us some c. And in order for c to be in the prime field, we simply just have to define this as c mod p. So we have to take the remainder of c with respect, so we have to reduce it so that it is within p. So whenever we do this, we will get a value c which is less than p. So therefore c is in the Galois fields. And then for the last one we have inversion. Inversion really is not that important, but it's interesting. It's just if you say the whole purpose is if you say a multiplied by a inverted, this will give us 1 modulo p. And you can find this using the extended Euclidean algorithm. Once again, not important to this, but if you want to read further into that, I put fuck ton of links in the description, and a few of them mention this stuff here. Alright, so that's prime fields, pretty simple stuff. Once again, this is prime number. This p here has to be a prime number, or I can just say here so it's prime number, so prime number of elements from 0 to p minus 1, and those are the operations there. Now for an extension field, or let me give you an example real quick. So we're going to be working with Galois fields, prime fields, with 2 elements, which is the smallest prime number. And we're going to be working with 2 elements because we're in comp size, so it's going to be bits 0 or 1. So let's say that we wanted to, so this is only going to be 0 and 1 here, the elements here. So let's say we want to do addition, so it was 0 plus a 1 can equal 1 in the Galois field. Or let's do the four possibilities here. 0 plus 0 is equal to 0, which is defined as 0 mod 2. 0 plus 1 is equal to 1, defined as 1 mod 2. 1 plus 0 is equal to 1, defined as 1 mod 2. 1 plus 1 is equal to 2, which is defined as 0 mod 2. Now you might see this pattern and be like, oh fuck, that is simply just A XORed with B, which is just the exclusive OR. So this only returns a value of 1 or true when one but not the other is active. So only in these 2 instances when we have 1 and 1 0. And what's also kind of cool is the subtraction is the exact same thing. So the inverted operation of XOR is simply just XOR. And you can kind of tell that just because that's just a comp-sci thing, but if you do an exclusive OR with the same element twice, you just get the original back. Because XOR just kind of flips bits, so if you're flipping the same bits twice, then you just get the original back. So what you're going to get is, in GF of 2, we have that addition and subtraction are just going to be defined as A plus or minus, or A XOR B. Multiplication will just be A and B. And then inversion, I actually haven't thought about this, but let's see. the inversion of 0 doesn't really have, there is no inversion to 0. However, I don't think inversion of 0 applies here. Yeah, that doesn't apply. But the inversion of 1 is just 1, so I won't talk about inversion because I'm not really sure about it. So yeah, that's just our example in the Galwa field of 2, the prime Galwa field with 2 elements, 0 and 1. Pretty simple stuff. We can relate this directly to computer science talk. Alright, now for the second type of field, extension fields. And this is going to be represented with a GF of a prime number to some integer, to some positive integer. So where m is greater than 0, and p is a prime number. And as the name implies, it's simply going to be an extension of the prime fields. So here the element representation is going to be a little different. The elements are not just going to be numbers, they're going to be polynomials. Polynomials are vectors, rather. So if we look at this as a polynomial, we're going to consider them as, so let's say we had an element ax, or just a, which is in the GF, or the Galwa field. The polynomial representation of this is going to be a, which is a constant, sub m minus 1, times x to the m minus 1, plus a m minus 2, x m minus 2, plus dot dot dot, plus a1x plus a0. And this is equal to a as a function of x. So this is a polynomial. Or we could also represent this as a vector. And that's just going to be a is equal to a0, a1, all the way up to a sub m minus 1. And these are both in the Galwa field. Now, the only constraint here is that we keep x as a variable. So if we look at the polynomial representation, x is just a variable. The coefficients, however, must be in the Galwa field, in the prime field of this. So for all a sub I, a sub I must be in the Galwa field of P, so the prime field with P elements in it. So for example, if we had, if we were looking at the Galwa field of 2 to the 8th, which is equal to the Galwa field of 256, which is what we will be using for AES, we're going to have 256 different elements, which is expected because every coefficient can either be a 0 or a 1. So every AI is in GF of 2, which is the prime number here, which is equal to just 0 or 1, which we have seen before. So one example of what this could look like is 1a of x could be, I'll just use a vector, bit vector notation. 1 0 0 1 1 1 0 0. That could be one bit vector. And as you probably know, we have 8 bits. That gives us 256 different combinations, which gives us the 256 needed elements to satisfy this requirement of the Galwa field having that number of elements there. Now for the operations, it's going to be a little different from the prime fields. So we will have, we'll start with the addition and subtraction. It's just going to be like normal polynomial addition. So polynomial addition slash subtraction. However, the only difference is you're going to combine the coefficients, but you're going to combine them using the prime field arithmetic. So combine coefficients using GF of P arithmetic. So for example, in GF of, let's say 2 to the 3, just to keep things simple. So let's say we had x squared plus x plus 1, and this plus, we're going to say x squared plus 1. You can also just say x squared plus 0, x plus 1, just for completeness. So what this is going to be is we're going to have a 1 plus a 1 for the x squared, plus a 1 plus a 0 for the x, and then a 1 plus a 1 for the constant. Now, you're going to combine the coefficients, so we're going to get a 2x squared plus x plus 2. And then we have to, this is not in the Galwa field of 2 to the 3 because the coefficients are not in there, are not in the prime field. So we need to reduce these, and we get a 0x squared plus x plus 0. This is just using the XOR, which is equal to x. Right, so you can also just skip this step right here, just by doing that, applying the XOR there. So this would give us a 0, then a 1, then a 0, which is what we got with the reduction. Alright, now for multiplication, it's going to be a little different, but the concepts are going to be the same. We're going to start by doing regular polynomial multiplication. So polynomial multiplication. However, this could produce something that's not in the Galwa field. So let's say we have in GF of 2 squared. Let's say we have an x plus 1 times an x. Is that right? Yeah. So GF of 2 to the 2, and we're going to say x plus 1 times x. Now this is going to equal, if we did the polynomial multiplication out, this is also one of the reasons of representing this as polynomials, just so we can do the multiplication here. We get an x squared plus x. Now this is not in the Galwa field of 2 to the 2 because we have an x squared there. So in order to make it in there, we need to reduce it. So in general, we're going to say that a of x times b of x is going to equal a c of x, which is going to be defined as c prime of x mod something that we can relate to as a prime, or something that we can call a prime. and these are going to be called irreducible polynomials. So mod p of x, where p of x is an irreducible polynomial. And what I mean by that is it cannot be factored. So no roots. And what was kind of interesting was when I was learning this stuff, I figured out that the way to tell if this was an irreducible polynomial for the Galwa field is if you plug in, so for so we're gonna have you know, let's actually just do this in GF of 2 to the 8, and then we'll do x to the 7 plus 1 times x, which gives us x to the 8 plus x, which is not in the Galwa field. So the irreducible polynomial for, or and one of the many, one of the is going to be this polynomial here. And it should also be noted that the degree of the irreducible polynomial, it goes up to m. So p of x has degree m. And it has to have degree m. It can't have anything less than, because otherwise stuff would be divisible by it. Or not divisible by it, but you would be able to have a C prime that is, you would reduce it by too much. So like, for example, if we chose an irreducible polynomial of degree 2, that would kind of cap our result of the multiplication to only elements in 2 to the 2, which is not what we would want. We want to be all the way up to, we want to get all 256 elements in the Galwa field. So p of x has to have degree m. So for AES, we're actually going to have an irreducible polynomial of is equal to x to the 8th plus x to the 4 plus x to the 3 plus x plus 1. And what I found was the irreducible polynomials that we looked at, or that were shown in where I learned this from, was that if you were to plug in the prime number into this polynomial, so we're going to say p, the irreducible polynomial plugging in p, we get p to the 8 plus p to the 4 plus p to the 3 plus p plus 1. But in GF of 2 to the 8, p is equal to 2, so we have p of 2 is equal to 2 to the 8 plus 2 to the 4 plus 2 to the 3 plus 2 plus 1, and that number is 213? No, not 318 something? No. Hold on, let me figure this out real quick. $283, which is in fact a prime number. So this is a prime number. So a pattern that I did find, I might not be backed up, but p of p, so if you plug in the prime number, gives a prime. That might be a sufficient condition or a necessary condition, I'm not really sure, but that's just one thing I kind of found. So yeah, there's that. So we get the full polynomial multiplication and then reduce it. So we say x to the 7 plus 1 times x is equal to x8 plus x, and this is equal to, or defined as some c to the x modulo the irreducible polynomial for the Galois field of 256. And you can find that using polynomial long division. It's just the remainder. So this is C prime. So C prime of x is equal to the remainder of C of x divided by P of x. Once again, you can use polynomial long division there. All right, so yeah, that is Galwa fields. So we looked at what fields were, what Galwa fields were, just a set of elements, a set of n elements, and they have to have 4 operations that produce elements within the Galwa field. Then we looked at a type of Galwa field, prime field, which has a prime number of elements, just takes the integers from 0 to p minus 1. And you just do the addition, subtraction, and multiplication using modular reduction, and then the inversion you can find using the extended Euclidean algorithm. Then for the extension fields, which is a prime number raised to an integer, we represent the elements as either a polynomial or a vector, and the addition and subtraction is simply just a polynomial addition subtraction, and then you can combine the coefficients using arithmetic from the Galois field. From the prime field there, and then for multiplication you do polynomial multiplication, and then you reduce the result using the irreducible polynomial. Give me 2 seconds. All right, so yeah, that's a bit of a mathematical basis. Now we're going to look at the actual AES algorithm. Alright, so AES, also known as the Advanced Encryption Standard, was an algorithm developed by I forget his name. Is that his name? Yeah, I don't know how to pronounce that. I think it's German. Rijndael. That is definitely not it, but it is. Oh, I don't know how to pronounce that. All right, either way, it was adopted by the American government early 2000, I think, or 2002, and it was originally called the Rijndael, that algorithm, this dude's name, and then it was adopted as the Advanced Encryption Standard, or AES, 2001 actually. So what it is it's a block cipher, or block cipher, which means that we're going to encrypt certain blocks of finite sizes at a time. So let's say we had some data, and it was 49 bits. Oops, what is this? It was 49 bits, or bytes. So we're essentially going to take this and we're going to divide it up into blocks of 16. So we're going to get 4 total blocks, because the last block will only have 1 active byte, but we still need to encrypt that as that last byte. So we're going to encrypt each block one at a time. So this is 4 by 4, 4, 4, 4, where each has 16. And then we have 1 plus 15 empty bytes, or just zeros. So that's what the block cipher means. We're going to encrypt 16 bytes at a time. Now, AES is also a round-based algorithm. So based on the key length, so the input, so AES is this. We have our plain text X. We put it in of how many ever bytes. We put our key in, and out we get out the ciphertext Y. And the key can be of 3 different lengths. So we have 128 bits, 192 bits, and then 256 bits. This is equivalent to, what is that? 16? No, not 16 bytes. Is it 16 bytes? Oh yeah, it is. So we have 128 bits is just 16 bytes. 192 is 24 bytes. And then 256 is 32 bytes. And this key length is indicative of what's up. I'm not even gonna pronounce that name. I'm sorry. I don't want to axe that completely. So this key length will indicate how many rounds we're going to do in the algorithm. So the 128 bits will give us 10 rounds. Dog's awake. 192 bits will give 12 rounds, and 256 bits will give 14 rounds. And each round has a certain algorithm that we're going to do, but most of the rounds will be the same. So I'll first go through what the 0th round will be. So we're going to have a round 0. Which is going to be just add round key. So I'm just going to call this add key. So most of the operations in AES will have just shortened names, just to make it more easier to kind of just write out, understand, and diagram. So we have round 0, which is just add key. Then we have rounds 1 all the way to the number of rounds minus 1. So I'm going to call number of rounds NR, N sub R. And in these, we're going to do a byte sub, then shift rows, then mix columns, and then add key again. And then for the last round, round NR, we're going to do a byte sub, shift rows, and then add key. Notice how in the last round we don't call mix columns. And then in between each round, we're gonna transform the key or get the next sub key. So I'll talk a little bit about that after, but we're essentially going to new key or transform the key. For these actual operations, I'm not just going to leave you blue-balled. I'll explain what these are. So for add key, it's simply an XOR operation, or we do each byte of the state. So we're going to call the state each one of these blocks. So each block will be passed in as an initial state, and then as we go through the rounds and encrypt it further, shuffle it further, they're going to be the same. It's going to still be called a state, but that's just going to be the state that we return at the end. So the state is just the text that we keep encrypting and shuffling and whatnot. So add key, we take the state and XOR it with the subkey. And this just means XOR the corresponding bytes. Now for byte sub, we're simply going to take each byte of the state and pass it through the what's called an S box. So state goes to the S box and that gives us the different next state. The S box is simply just a box or a substitution table that it's just an array of values, and you pass in so it's an array of 256 values, since we're using bytes here, so 256 possible values. So we pass in the value of each byte, and it will give us the substitution for that byte. So each byte has one specific substitution, and it's a fixed matrix, so we can just store it in our program. And this S box was calculated. It's not just random. It was calculated by finding the inverse of the specific element in the Galwa field of 2 to the 8th, and then applying what's called an affine mapping. I'm not going to go into detail here, but once again, I posted a bunch of references down below. So you just pass the state through the S box. And then for shift rows, we're going to take each row, so we're going to kind of model the state as a 4x4 matrix. So 1, 2, 3, 1, 2, 3, and then we're going to shift the first row by 0, so nothing. Then shift the second row by 1. Shift the third row by 2, and shift the fourth row by 3. And we'll see how this works in code. It's going to be pretty simple to implement. And then finally, mixed columns is going to be, we're going to keep it in this notation, in this matrix notation here of the 4x4 table, and then we're going to multiply it by another fixed matrix. So we're going to take the state and multiply it by a 4x4 fixed matrix. And we're going to call this the mixed calls matrix here. And that's just going to give us a value that will be the next state. So yeah, these operations are going to be the same. So whenever add key will always be the same, depending on the parameters we pass it in, but it's always going to do the same thing no matter the round. Byte sub, same stuff. Shift rows, same stuff every round. And then mixed columns, same stuff every round. Now, when I was talking before about the keys, the transforming, we're going to be following what's called a key schedule, which is the last link that I posted. I posted a link over here. Yeah. So this is the key schedule. Let me just get this here. And I mean, I'll also show you the more detailed outline for the actual algorithm. But this is the key schedule, and this is also dependent on the key length. We're only going to be looking at the 128-bit key schedule today, but I'll put the other ones in there as well when I figure that out. So it's just, we take a few transformations and then do a bunch of XOR operations using the key. So you pass in the key and it will give the same key schedule no matter what. And then I'm just going to go to where is it? This thing right here. So yeah, this is a detailed detailed diagram of how each round will work. So we first take the byte substitution. So take all 16 bits or 16 bytes here, pass it through the S box, pass each one separately through the S box. Then we take the bytes that come out of that, the substituted bytes, shift around the rows, which gives us another 16 bytes. The mixed columns, matrix multiplication, and then we get another 16 bytes. And then finally, the key addition is just an XOR operation with each byte of the key, of the subkey. And each subkey is 16 bytes, that is regardless of key length. So the key schedule is different for each one, but it will produce a specific amount of subkeys. And that specific amount is equivalent to the number of rounds. So for 128 bits, or it's going to be the number of rounds plus 1. Because if you look again over, where is it? Just need to find this. Here we go. So the first round 0, we add the key. So every time we add the key, we want to transform the key. So we will have the number of rounds plus 1, that we'll need that number of keys, and each key is going to be 16 bytes no matter what. So yeah, this is the key schedule for 128 bits. Then we have the 192, it's a little bit more complicated. And then the 256, which is much more complicated. Alright, so yeah, that is going to be that. So let's go ahead and write some code. We're first going to start in cmathematics.h, just because I want to write a few reference methods real quickly first, just that we will need, and these are general ones, so that's why I want to put it in cmathematics.h. So we have here, so we're going to have three methods. One's going to be void reverse array, and this will take in an unsigned char character pointer array, and we're going to pass an integer start and an integer end, or integer I and integer f. So this is just going to reverse an array between the indices of I and f. Then we're going to have two rotation methods, so void left rotate, which is an unsigned char pointer array, and this is going to shift the array left by d positions, so pass an integer d and also the length as len or n. And then we're also going to have void right rotate, unsigned character pointer array, integer d, so right rotation by d positions, and the length is integer n. Alright, so now in cmathematics.c we can copy and paste these signatures over. So for reverse array, we're simply going to do an algorithm that you probably could have learned, probably should have learned a long time ago. Or, I mean, if you didn't, it's not too difficult. You simply just, you only look through one half, and you just kind of swap each element with its counterpart on the other side. So if you were to put a mirror in the middle, you just take the elements, or not a mirror, but you would take the elements the same distance from the middle and just swap them. So we're going to say for integer I is equal to, or no, we're going to, this is, I looked at this online, so this is, I'm just taking this pretty much from online. I mean, it's a pretty common algorithm. So we're going to say while I is less than f, so while the start index is less than the final index, we're going to say unsigned char t temp is going to equal to the array at I. So the first element, then we're going to say array at I is equal to array at f, and then array at f is equal to temp. So we're simply just swapping corresponding elements across the median, or across the middle. And then we want to say I plus plus and f minus minus. So we just approach the middle from both sides. Now for left rotate, we're going to use the reversal algorithm. So we're going to have, what we're going to do is, we're going to say reverse array. I'm not going to explain this. It's just, if you want to look it up, it's elementary stuff, but it's completely unimportant here. So we're just going to call reverse array, passing the array. We're going to first reverse from 0 to d minus 1. Then we're going to reverse the array from d to n minus 1. And then we're going to reverse the entire array. So array from 0 to n minus 1. Now right rotation, there's a little clever thing you can do, is that right rotation is simply a left rotation by the complementary number of positions. So we're simply going to call left rotate on array, and the number of positions to shift is length, or is n minus d, and the length is still n. So you simply just, because if you have, let's say you had a circle with 4 sections in it, and you rotated it counterclockwise by 1 position, that would be the same as rotating it clockwise by 3 positions, which is 4 minus 1. So you're simply just rotating it the supplementary number of times. Alright, so yeah, that is utility methods that we'll need for the arrays. Alright, so now let's go and create 2 new files, aes.h and aes.c. We're going to start in the header file. And we're going to include cmathematics.h. Let me see, do I do the same thing? Yes, I do. Alright, so include cmathematics.h. We're going to have a few macros here. So if not defined, AES-H, define AES-H, and if. So that's the macro for the file. Then we are going to say, we're going to define block length as 16 and define block side as 4. So block length will just be the length of each block that we want to encrypt, and block side will be the side length of the matrix. So 4 by 4. Then we're just going to have 3 values just for neatness. Define AES 128 as 128, define AES 192 as 192, and then define AES 256 as 256. I'm just doing that just for, just because I want to be cool. I don't know, I just put that there. Alright, so now we're going to have a few reference tables. So these are going to be values. Oh, I didn't make a paste bin, I should have. Alright, let me do that right now actually. Just because I don't want to have to show you guys how to do this, I'm just going to do it. Alright, come on, paste bin. Syntax highlighting C, paste name AES, encryption or AES reference tables. Create new paste. And then I am putting this paste or the link in the description right now. So reference tables. This will also be on the GitHub if you're watching this after. That might be easier. Alright, save, and then now I need to figure out where this is. It's going to be pastebin.com/y8377RA7. Alright, perfect. We actually won't need this for a few seconds because we're not in the source file yet. Alright, but in the header file we're going to define these arrays or these tables as externals, just so we can have them in multiple files. So we're going to have the substitution box, and that will be an extern unsigned character, and it's going to be called sbox, and it's going to be of length 256. Now 256 because 1 byte 256 possible values, so we need 256 possible substitutions. And then we're going to also have the constant matrix for mixed columns, and we're going to call it extern unsigned char mixed call matrix, and it is a 2D array with dimensions block side and block side. Make sure that these are block side and not block length. Alright, we can actually now go into the source file, and I'm going to go into AES.c. We're going to include AES.h, and then we're going to paste in the definitions here. So substitution box. Damn it. My dog needs to stop barking. And then the constant matrix for the mixed columns. Just like that. Alright. Before I forget, we can also hang out in the source file for a second and just do some 3 includes. We'll need include stdio.h, include standard lib.h, and then include string.h. Just so we have that for later on. So stdio, standard lib, and then string. Alright, so those are our reference tables. We're going to add to this when we do decryption, which will just be the inverse of these. And we'll talk about that later on. Alright, now we're going to have some more utility methods. And the one we're going to have is going to be Galwa field multiplication. So perform Galwa field multiplication of 2 bytes in the extension Galwa field of 2 to the 8th. So it's going to return an unsigned char, and we're going to pass in G, and it's going to be called gmul, whatever, Galwa multiply of unsigned char G1 and unsigned char G2. So I'll copy the signature in. We're going to need to know how to do this, and this is going to be following the polynomial multiplication algorithm that we had. We're going to need to know, we're going to need a method for this, because when we do the matrix multiplication, which is right over here, that's going to be additions and subtractions and multiplications, but they are going to be in Galwa. So this is matrix multiplication in the Galwa fields of 2 to the 8. Alright, so let's copy the signature over, and we will write this. Alright, it's already copied. Perfect. Alright, so I got lazy, and I also didn't know how to do this, but I took this algorithm from Wikipedia. I'll put the links on this here. But essentially, we're going to store the results. So unsigned char p is equal to 0, and then we're going to do a loop and then return p. So in this loop, we're going to say for integer I is equal to 0, I is less than 8, I plus plus, 8 being the number of bytes. So we're first going to say if G2, and 1. So this essentially means if the LSB is active. And the reason why is because this is 1 is just 0, 0, 0, 0, 0, 0, 0, 1. So if you bitwise AND that with G2, you will get the least significant bit. Just consider the 1 as a mask. So if the least significant bit is active, then we're going to want to multiply. Or we're going to want to add. Because if the least significant bit is active, that means that we have a 1 in the polynomial. So equivalent to a 1 in the polynomial of G2. So we're going to say P XOR equals G1. So this is essentially just P plus equals G1 in the Galwa field of 2 to the 8. Because remember, addition is simply just adding the polynomials, but we're just going to use GF, the prime field for the addition of the coefficients. But if we look at it as a bit vector, we are simply just adding the bits in the bit vector. So if we go back here, if we look at it as a bit vector and we wanted to add 2, we would simply just perform an XOR on all of the bits. Which is also why add round key is called add round key, because we're simply just taking an XOR, which is addition in this Galwa field, in the AES Galwa fields. So we're going to add G1, which is just kind of makes sense because if we're multiplying it by a 1, that's good. Alright, then we're going to try and see if the most significant bit is active in G1. So Boolean, the most significant bit is equal to G1 bitwise AND with 0x80. So MSB is if G1 is greater than or equal to 128. Now 0x80, that's going to be if the, which is equal to 0, 1, 0, 0. So that's this right here. 0x80 is just 128, which is just the 7th bit active. So if this returns a value, then we know that the most significant bit, or not the most significant bit, but a high bit is set. So we'll call this actually a high bit. And if it is, then we want to reduce. So we're first going to say G1 left shift equals by 1. So we're going to be rotate G1 to the left, which is multiplying by x in the AES Galwa field. And then we're going to say if the high bit is active, then we're going to say G1 XOR equals with 0x1b. Now what is this statement here? This is the reduction statement. Must reduce. Now how is this a reduction? Well, let's look at what this value 0x1b is. I can actually go into the header file and say, define this here. So I'll say hashtag define AES irreducible as 0x1b. Right? Yeah, 0x1b. So this is just essentially saying we're going to subtract minus equals 0.0011011, which is equivalent to taking the modular reduction of x to the 8 plus x to the 4 plus x to the 3 plus x to the plus x and then plus 1, which is equal to the AES irreducible. So we are simply just subtracting the AES irreducible polynomial, but only the value that is less than, only the value that we can see, because we can't see the x to the 8 in 1 byte because we only have 8 bits. So I'm just going to do XORed with AES irreducible. And then after that if statement, we're going to say G2 right shift equals by 1, which is just rotate G2 to the right, which is divide by x. So this kind of makes sense because as we're moving through G2, so we're moving G2 to the right, so we're dividing by x each time, we're multiplying by x in G1. Alright, so that is Galwa field multiplication. Once again, I will put the link to this source code down below, or in the code actually. Alright. Let's get to the encryption layers now actually. So I'm going to go to the header file, start a new section. So all of these are going to return void because we're going to be passing in pointers, so we can just modify them directly. Alright, we're first going to say void add round key. This takes an unsigned character state, and it's going to be block side, and an unsigned character subkey, 2D array, block side, and block side. I actually want to test something out here. Can I do a bit of this type def unsigned char block side, and I want to name this as AES block. Can I do that? I don't think so. Okay. Yeah, that's fine. So yeah, once again, we're representing the key and the state as a 4x4 matrix. Alright, so add round key. Then we're going to say void byte sub. This takes an unsigned character state of block side. So I'm just going to copy this parameter, the state, which is once again the text that we're encrypting. Then void shift rows just takes in the state, and then void mix columns just takes in the state. So notice how the only layer that will take in another parameter is the add round key, and that is because we need to add the subkey to the state each round. Alright, so let's copy this, copy all the signatures, paste them in. We'll start with add round key. Once again, these are going to be pretty straightforward, nothing too crazy. So add round key is just going to be a add in the Galwa field, or in the AES Galwa field, the corresponding bytes of the subkey and state. So we're just going to iterate through each row and each column. So 4 into r is equal to 0, r is less than block side, r plus plus. 4 into c is equal to 0, c is less than block side, c plus plus. Then we're going to say state at I or at r at c XOR equals with the subkey at r at c. It's as simple as that, and that's the whole method right there. For byte sub, it's going to be the same exact loop, so we can actually just copy the loop in there. Except this time we're going to say that state at r at c is going to be equal to the s box value, and for the index it's going to be state at I at r at c. So we're taking the current value, and this should just be state. Here I'm just gonna. So we have the loop that goes 4 by 4, so each row and each column, and then state at r at c is equal to s box at state at r at c. So we're simply taking this value of the state and passing it into the s box and getting the substitution and assigning that back to the same position. For shift rows, it's going to be same type of stuff. It's going to be, once again, self-explanatory. So we're just going to rotate each row according to its position. So for integer r is equal to 0, r is less than block side, r plus plus. We're just going to call left rotate. And the row to be rotated is going to be state at I, and that returns a pointer, an array of size 4 here. So we're going to rotate that by I, so the number of positions to rotate is the index of the row, so I, and then the length of it is going to be block side. Or this should be state at R, and the number of positions to rotate is also R. All right, now for mixed columns, this is matrix multiplication. We're going to take a matrix and we're going to store the output, because we can't just read new values right into the matrix, because for matrix multiplication, which you may or may not have learned, you need all the values of both original matrices in order to determine the correct output. You can't do this procedural, or you can't we can't write to the state as we find the values, because that will incorporate those new values into the calculations that we're doing later or right after. So we're first going to get an output, so unsigned character output, and this is going to be a 2D array, block side, so another 4 by 4. Alright, so this is it's going to be matrix multiplication in GF of 2 to the 8. So what this means is multiplication becomes calling Galwa multiplication, and addition becomes XOR. So we're going to do our matrix multiplication algorithm, which is just, so it's going to be another 4 by 4 for loop. So 4 integer r is equal to 0, r is less than block side, r plus plus. And for integer c is equal to 0, c is less than block side, c plus plus. So each element of the output matrix. So we're first going to set clear to 0. So out at R at C is equal to 0x0, 0. Now each element is going to be the result of the dot product between the rth row of the mixed column matrix and the cth row, or the cth column of the state. So dot product of the rth row of mixed column matrix and the cth column of state. So dot product is just going to be in a loop. So for integer I is equal to 0, I is less than block side, I plus plus. We're going to say out at R at C. This is going to be equivalent to a plus equals, but we're going to be doing XOR equals with G multiplication, so Galwa multiply, and we're going to multiply mixed column matrix at R at I with state at I at C. So it is essential that you get this order correctly, or the mixed column matrix and state can be swapped, but these indices must be the same. So we are getting the ith element of row R from mixed column matrix and the ith element of column C from the state. And when we just add these together, we just get the dot product. All right, and then after the 3 nested loops, we're going to copy the memory over. So copy memory to the state. So memcopy, that's why we needed string.h. The destination is going to be state. Origin source is going to be out, and the number of elements is going to be block side times block side times the size of an unsigned char. All right, so a few notes here. We don't need to call free on out because it's a heap variable. So it just gets freed once we're done, and it's also an array, so it automatically gets freed. It's not a pointer that we called malloc with, because if we did call malloc, then we would have to call free. And then for the memcopy, I can just say copy all 16 elements over, because 2D arrays are simply just 1D arrays just with different indices. So it's stored as consecutive elements in the memory, but access the indices differently. All right, so that's mixed columns. That was the matrix multiplication. All right, now we're going to move to the key schedule. So we're going to hop back in AES.h, and we're going to start a new section, key scheduling. So when I first wrote this, I didn't bother with the way that this document here lays it out. Is you're going to generate all the subkeys at one time. When I first did this, I was like, oh, you don't need that. You don't need to store how many ever bytes that is at the same time. You can simply just generate the key for each round. And yes, that works, but only for 128-bit keys, because the next key is only dependent on the previous key and nothing else. Whereas when we go to this one, we have dependence on the last key, but also the previous key, and then the same thing for 256. So we need to generate all the subkeys at the same time. And also, this helps for decryption when we need to walk backwards for the key generation. All right, so for key scheduling, we're just going to have 2 functions for now, but we're going to have more later on. So the first one's going to be void generate key schedule, and we're going to pass in an unsigned character pointer in key. So this is just going to be the key as a string. Then we're going to say pass in integer key length, so the length of the key, which is indicative on how many subkeys we generate, and then the output will be unsigned character. So this is, we're just going to pass in a pointer, and it's going to have an empty first dimension, and then block side and block side as the last one, or as the last two. So it's going to be a 3D character array. I'm going to think of this as an array of variable length of 4x4 matrices, which is this part here. So the 4x4 is the block side by block side. That's just each subkey, and then this first dimension will just be the array of those matrices. And then we're going to have void generate key schedule 128 pass in unsigned character pointer in key, and then this will output to an unsigned character. And the first dimension here is going to be 11, not 10, remember, because we have 0 plus 10 rounds. The first round we still needed a new key, so 11 of block side by block side. Alright, so I'm going to copy and paste these signatures. What's up with this? Unnamed prototype parameters not allowed when bodies. Oh, I didn't even name the. Yeah, okay. I didn't give names to the arrays there. I'm just going to call it a subkeys array. Alright, so for generate key schedule, we're simply, right now, we're just going to call generate key schedule 128, pass in the in key, and then just pass in subkeys. Just because we're only going to be worrying about 128 for this video, but I'll add in the other key schedules later on. Alright, so for the key schedule in 128, we're going to look at this document here. The first key, so round key 0, is going to be the original key. It's just going to be the key that we pass in. So round 0 takes in the original key. So it's just going to be we're going to iterate through the characters of the key here, and we're just going to put them in column by column. So it is important that we do column by column, and this will also apply to when we read in the bytes, because when we call shift rows right here, the bytes go down. So it's B0, B1, B2, B3 in the first column, not the first row. So when we call shift rows, we need to do it this way. So we have the rows as 1, 5, 0, 4, 8, 12, then 1, 5, 9, 13, then 2, 6, 10, 14, and then 3, 7, 11, 15. So we're going to have a counter integer I is equal to 0. Then we're going to iterate column by column first, then row by row. So for int c is equal to 0, c is less than block side, c++. Then for integer r is equal to 0, r is less than block side, r++. And then each element will simply just be subkeys at r at 0 at r at c is equal to in key at I++. So we're taking the 0th round 0, so this 0, the first dimension, corresponds to the round number, and then the element is rc, and this time we're using row major notation, but we are reading in as column major. And then the in key, we're taking the ith character and then incrementing the character there. Alright, and then from now on, we're going to need a round coefficient. So unsigned character, round coefficient. And this is going to start as 0x01. So now we're going to iterate through each round. So it generates each round. So for I is equal to 1, I is less than 10, or less than or equal to 10, I plus plus. We're going to transform the key for each round. First thing we're going to need is a 4D or a 4-byte array called a G. So unsigned character G of length 4, and it's going to have 4 different elements that we will put in. And looking at this diagram, which is over here, the function G takes in the last 4 bytes of the previous key, so these 4 bytes right here. As you can see, it takes in W3, which is the last 4 bytes of the last round's key. And then we're going to shuffle the bytes, so left shift by 1, get this over here, and then we're going to pass it into the S box, so get the substitution, and then we're going to XOR it with the round coefficient, only the first byte though. So I'm just going to do this in one fell swoop here. The first byte of G will be the S box of subkeys at, now the round number will be I minus 1. The column will be 1, and then the row will be 3. Right? Or no, sorry, row will be 1, column will be 3. Because this is the third column there. Right there. So first row, third column, because once again we're shifting to the left, and then we want to XOR this substitution with a round coefficient. And then here, from here on out, it's going to be S box at subkeys at I minus 1, so still the I minus 1 for the round, the previous round. Then this time it's going to be row 2, column 3, no XOR, and then we have S box subkeys at I minus 1 at 3 at 3, and then S box at subkeys at I minus 1 at 0 at 3. Alright, then we can we're going to insert this G into the subkeys. So for integer r is equal to 0, r is less than block side, r plus plus. And here we can't just insert G, we have to XOR it with the first 4 bytes of the previous key. So it's going to be for integer r, and then we're going to say subkeys at I at r at 0, because 0 with column is equal to subkeys at I minus 1 at r at 0, XORed with G at r. So we're XORing the corresponding elements there. And then we're going to XOR for the last 3 words, so the last 12 bytes. So for integer c is equal to 1, c is less than block side, c plus plus. Then for integer r is equal to 0, r is less than block side, r plus plus. Here we're going to say subkeys at I at r at c, so pretty much the same indexing as before, except this time we're just going through the last 3 columns, since it's going to be the same procedure for the rest. And this is just going to be is equal to subkeys at I minus 1, so still the last round, at r at c, XORed with subkeys at I at r at c minus 1. So what we're doing is we're taking the subkey in this position from the last round, and then we are XORing it with the previously generated word. So W6 will be the output of W2 XORed with this the output of this right there. All right, and then outside of this loop here, well, we're still going to be in the round loop. So the last statement of the round loop of each iteration should be to increment the round coefficient. And the round coefficient is just going to be, for each round, the coefficient will be x to the I minus 1. So round 1, we have x to the 0, which is just equal to 1. Then we have round 2, x to the 1 is equal to x. Round 3, x to the 2, which is just equal to x squared. And then we keep going on, but we can't go to x to the 8. So round, 9? It's going to be x to the 8, which we're going to have to define as x to the 8 modulo p of x. So instead of just moving it up by 1, we're going to multiply by x. So this is going to be round coefficient is equal to g Galwa multiply, and we're going to multiply the round coefficient by 0x02, which is simply just multiply by x. Alright, and just like that, we have our key schedule generated. Alright, last part of this, we're going to be doing the actual encryption methods. So we're going to be wrapping up all the layers that we've written, and we're going to be writing the actual encryption methods. Let's go to AES.h, and we're going to have two new methods. First one is going to be an return type void. It's going to be called AES encrypt block. It's going to take in an unsigned character in text, and this will just be or should I, or no, this has to be a pointer, yeah. And we're gonna pass in a length of n because it may be an incomplete block. You never know. So in text int n for the length of the block. Then we're going to have the subkeys array, so unsigned character subkeys. It's going to be a 3D array. First dimension is variable, and then we have a block side by block side. And then this will be an integer number of rounds. That's once again indicative on the key length. And then we're going to have an output array, so unsigned character out, which is just a 1D array of length, block length. And then we're going to have the general method void AES encrypt, pass in unsigned character state, unsigned character pointer in text, so a string, integer n for the length of the string. Then we're going to have an unsigned character pointer in key for the key, integer key length, and then unsigned character double pointer out. So we're going to need a reference to a string, essentially. That's why a double pointer. Single pointer would just be a string, but we want to have a reference to that string so we can allocate the necessary memory there. Alright, so let's start with AES encrypt block, or first I have to copy these over. So for AES encrypt block, once again, we are already assuming that this subkeys array has been populated using generate key schedule. So what we're going to do is we're going to represent the state and key as a 4x4 table reading into columns. So we're going to have an unsigned character state. It's a 4x4, so block side by block side. And we're going to do something similar that we did with the keys, where we have a counter and then just reading column by column. So integer I is equal to 0. And for integer c is equal to 0, c is less than block side c++. And for integer r is equal to 0, r is less than block side r++. And we're just going to say that state at r at c is equal to I++, or I is less than n. In that case, we're going to take in text at I++, so we want to increment I, otherwise take a 0, because we don't want to read invalid memory. So just make sure that there is text to read, using the ternary operator there. Alright, so we're first going to start with round 0. So now that we have read in the state, we are ready to go. So round 0, which is simply just add the key. So add round key, and we're going to pass in state and subkeys at 0. So subkeys at 0 is simply just saying take the 0th 4x4 matrix of subkeys, which is just the subkey for round 0, the 4x4 key. Then we're going to do our for loop, so rounds 1 to nr. So for integer I is equal to 1, I is less than or equal to nr, which is a parameter we pass in, I++. Alright, so for each step we're going to do a byte sub, so byte sub pass in state. Then shift rows pass in state. Now if I does not equal, or you know what, I'm just gonna, I don't want to do that. I want to keep this neat. So this goes from rounds 1 to nr-1. So byte sub state shift rows state, and then we're going to add the round key, and we're passing in state and subkeys at I. So once again, same reasoning, we're taking the ith subkey there. And then round nr. So we're going to do a byte sub state. Oh, I forgot something here. Byte sub shift rows in the loop. It's byte sub shift rows and then mix columns. State. Now for the last row, or the last round, it's going to be byte sub, then shift rows, pass in state, and then add the round key. State and subkeys at nr. So the last subkey will be nr. And once again, it goes up there because we have nr plus 1 subkeys. And then finally, we're going to copy the bits. So copy bits of the state into the output, column by column. So I is equal to 0, just reset the counter. And then for integer c is equal to 0, c is less than block side c++. And for integer r is equal to 0, r is less than block side r++. And then we're just going to say out So the output at I++ is equal to state at R at C. All right. Now for the general method, the general encryption method. First, want to determine the number of rounds. So we're going to do an integer nr is equal to 10 by default. So we'll say switch keylen case 192 nr is equal to 12. Case AES 192, just using that macro. And then break case AES 256 nr is equal to 14, and then break. So that's just determining the number of rounds. Now we're going to generate the key schedule. So this is going to be a weird allocation here. So because we don't know how many rounds we're going to have, the array is going to be of a variable length. Now in C, we can't really declare that. We can't just say, we need to have that set up. So what we're going to declare is a pointer to a 2D array, which will just be a pointer to pointer to the first element of a 2D array list. So we're going to say unsigned character. Now the syntax is extremely important. Then in parentheses, star subkeys. So that's just the pointer. Good stuff there. Now we're going to have the 2D array of size block side by block side. So it's going to be a pointer to a 4x4 matrix. The pointer to the first element in a 4x4 matrix list. And this is going to be equal to malloc, and we're going to say nr plus 1 in parentheses times the size of an unsigned character array, 2D unsigned character array, block side by block side. Alright, good stuff there. So nr plus 1, once again, because we need nr plus 1 keys, and this is just the size of one key. Alright, and then we're going to generate into this pointer. So generate key schedule, call the general method, not the 128, and we're going to pass in the in key as in key, the key length is key length, and the subkey array will just be subkeys. Alright, now we want to divide up the input into blocks. So we're first going to get the number of blocks. So integer number of blocks is equal to n right shifted by 4, which is just simply n divided by block length. And then integer extra is going to be equal to n bitwise masked with 0x 0f. So n and 0x 0f, which is simply just n modulo block length. That's just a little trick. If you have a power of 2, you can just apply a bit mask to get the remainder. And then we're going to say the integer out length is going to be equal to number of blocks times the block length. Now we're going to actually allocate the output. So allocate output. So we got the output length. Then we want to consider if there's any extra. So if extra, we're going to do out, but you're going to reference out. Or we can say, dereference out and say the dereference of out is equal to malloc, then number of blocks plus 1 times block times the size of an unsigned chart. So we are doing number of blocks plus 1 just because we have an incomplete block, so we need an extra there. An extra whole block, and then we just do block length times the size of an unsigned character. And then we want to say the output length plus equals block length, just because we have that extra one. And then to avoid the if statement later on, we're just going to encrypt the extra text now. So what we are going to say is, let me actually write this down. Let me do this down here. So I'm going to insert table. So let's say this is our input text, and we want to have this as our output. So we're going to start at position 0, and that's just going to be the position of in, which will just be the same address here. So let's say this is 0x0. Then one block later will be 0xf, I believe. Yeah, 0xf. Then we'll have a 0x. Wait, is that right? No, it's 0x10. Then we have 0x20, and 0x30, and 0x40. So we're simply bumping it up by 16 every time. And then if we have any extra, so let's say this is unfinished, then we're just going to add the number of complete blocks times 16 to get to this, the unfinished block. And it'll be similar for out. So for the extra text, we're going to say AES encrypt block, since we're doing each block now. Now the in text will be in text, do some pointer arithmetic, plus the number of blocks left shifted by 4, which is just multiplied by 16. The numbers in this block will be extra, that's just the number of extra characters, and then the subkeys array will be subkeys, number of rounds is NR, and then the output will be a dereference of out plus number of blocks left shifted by 4, once again multiplied by 16. So you're going to see why this is a, once again, double pointer, because we want a pointer to a string so we can allocate in this method here. Because it's not, we're not always guaranteed to get an encryption, a cipher string the same length as the input, because they're cladding issues. So we're going to want them you want to allocate in this method, in the AES encryption method. All right, so that's the extra. Otherwise, we're just going to allocate. So the dereference of out is equal to malloc number of blocks times block length times the size of an unsigned character. All right, and then after this, we can encrypt the complete blocks. All right, so we're going to say for, let's do for integer I is equal to 0. I is less than n, and then I left shifted equals by 4. So we're just going to advance the cursor 16 positions every time. So we will say, and in each iteration we're going to call AES encrypt block on the in-text plus I, so the cursor is just I. N will just be block length since these are complete blocks. Subkeys is just subkeys, number of rounds is number of rounds, and then the output is just the dereference of out plus I. Alright, just like that, and then afterwards we can just return out length. And just like that, that is AES encryption. Good stuff. Alright, let's play around with this a bit. So we're going to include the AES header file. Then we'll have what's the encryption thing that or the test that I put down below? Give me 2 seconds to find this. There we go, online test. Desktop. So key size in bits, hex. Now this, what I found was I might be incorrect on the padding situation. Just because I don't know how to pad it to a full block, but I'll look that up. But for now, we're good with. I'll just do complete blocks just so there's no confusion. So let's actually go into here, and we'll have character pointer text is equal to random 32 characters. It's 20. 27, 31, 32. Then we're going to have our key, which must be 16 characters. So key is equal to, let's do an A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q. Is that it? Right? 17 selected. Ah, yes. All right. All right, 16 selected, and then we're going to have a character pointer cipher, which is equal to null for now. And then we're going to call AES encrypt. The in text is text. The number of characters is going to be 32. Key length, or key is going to be key. Key length is going to be 16. And then the output is just going to be a reference to cipher. Because once again, we want to allocate at this address within this method here. Alright, so then we're just going to do some print. I want to print out in hex. So I'm just going to grab a method real quick from GitHub that I wrote. Give me 2 seconds. What file is this in? Is it in here? No, it's in, alright. I'm just doing this for testing purposes. You don't need to do this, but you can if you want. Nope, not there. C, AES, AES.c. Here we go. So I just have a method here that will print out a string in hexadecimal things. So I'll want to print out plain text, then print character array, pass in text 32 false. Because if you don't use an IDE like me, you can forget that. Uh-oh. There's an infinite loop. Where is this loop at? I mean, I guess I just walk through it. Where are we? AES encrypt. Number of rounds is 10. Alright, generate key schedule is not the loop, or not the infinite loop. Okay. 2 blocks. No extra. So we go to the else, good stuff. Ooh, why is... It's not incrementing for some reason. I don't like, why is it not doing that? Maybe I do I is equal to I left shifted by 4 maybe? Nope. Alright, I'm just gonna do this. So for the loop, if this doesn't work for you, just do I is equal to 0. I goes from 0 to number of blocks, and then I plus plus. And then for the cursor, we're simply just going to replace I with I left shifted by 4. So when we say in text plus I left shifted by 4, do that same thing for out. So I in text plus I left shifted by 4. Make sure the I left shifted by, make sure the shift is in parentheses too. Okay. I hope that works. Alright, oops. So we have our online. Oh, did it not work? Alright, so our test, we have, this is the text here. This is the key, 128 bits, output hex. Alright, 3B752E, you get the point. This thing, I don't know why, but this is kind of weird shit. But yeah, it goes up when it encrypts a lot of extra stuff, I guess for padding, maybe? I don't know. But anyway, it works. That's kind of all you need to know. But yeah, cool stuff. That's AES encryption. Next time we'll be working on decryption, which is another bit of an adventure, but we will get through it. And yeah, So I hope you guys enjoyed. I'll put some more links in the documentation here when I get the chance to work on that. But yeah, hope you guys enjoyed, and I will see you guys next time. Have a good one.